Now we are looking at a way to get displacement from a velocity time graph. So what is velocity time graph? Velocity along the y-axis and time along the x-axis. In velocity time graph, the area under the curve represents the displacement over a given time interval. So let me explain this. The first thing is we are looking at velocity time graph. So what does it mean? We have velocity along the y-axis and time along the x-axis. This is time and this is velocity. Right? So if we consider any curve, okay, so that's your velocity time graph. Now we're looking at displacement, the idea of displacement from this graph. So if we happen to consider some curve like this, the area under that, what does it mean? So area under that, all I have to do is say, I need to consider 2 points, say point T1 and say T2. So this has to be so actually. You need to project it properly. I don't have T2. Let me make this as T2. So not good. Okay, if we consider this as T2, this is the point. Perfect. Now, area under the graph mean this space. This is an example of area under graph. When it comes to velocity time graph, if you calculate the area under the graph, you'll end up with displacement. Okay. And what else? We need to show the math as well. Math proof. Okay. Let me do this for you guys, the math. See, first thing is I'll explain area of a, actually not explain, we'll discuss the area of a rectangle, simple one. We'll start off with a simple, most simplest structure. So this is the length, this is the height. Area will be length into height. If you want to call it as breadth, length into breadth. Right? Same thing over here as well. Length over here is time, height over here is varying velocity, yes. But yes, if you add them up, if you add this varying scenario, you'll end up with displacement. Okay. So in this case, instead of this, it is velocity. The heights are velocity and length will be time. So what is velocity into time? Velocity in time is your area. Technically, it's area only, and it is displacement basically. This is the whole funda. That's why we consider area under the velocity time graph as displacement. So when you have to add this, so basically it's not rectangle. So what now? But the concept does not change actually. I can consider redraw this as combination of say rectangle and a triangle, right? Something like this. We'll get an approximate value. But if you want to get an exact value, we need to get an expression for the velocity, right? So v of t. And then what we have to do, how do you get the displacement? How do you add up anything that is varying? Yes, we have to integrate it. Integrate is a fancy way of talking about addition. So that's where we use integration. If it was a simple Sida Sada graph, what can we do? we can just use area of triangle and area of rectangle concept and add them up. But if it's varying and you know how the velocity is varying, if you get an expression for that, if you are able to mathematically express that, we can use integration to figure out the area under the graph. We'll do a few set of questions. Okay, so yeah, velocity time graph and displacement. Under velocity time graph, we saw that we recapped that velocity is along the y-axis and time is along the x-axis. The area under the curve represents the displacement. That is a simple, straightforward proof. So we know that area is length into breadth. In case of a velocity time graph, the area will give us, actually let me do that properly. Do this properly. In velocity time graph, the same rectangle, if it's there, along the length, it would be what? Along the length, it will be time. And along the height, it will be correct velocity. And if I consider the area, this will be velocity into time. But we know velocity into time is nothing but your displacement. Right? Then we tell, but we know that velocity in time is displacement. And therefore, this is area. Area under the graph is equal to displacement in case of a VT graph. Not everywhere, remember. This is a specific case. So that's your mathematical proof. Okay, so I wanted to make one more point. Yeah. So one more key idea here is integration. So if the structure is not, say, rectangle, if it's some weird thing like this, what do? End of it, we need to add. There's nothing to it. Multiplication is repeated addition. Right? Multiplication is repeated addition. So we are going to add repeatedly the area, this area, this area, this. You can imagine that they are made up of bunch of rectangles like this without gap actually. So you can imagine rectangles like this, but their height varies. The thickness is the same, but the height varies. So what do? We use the concept of integration. So dt represents your width and this represents your height. And that's that. Okay. So I think, yeah, I'm done.